Hello and welcome to Tonight at 8 from the RSGB. We're all getting used to seeing SDR technology at the heart of modern amateur rigs. Jack Purdum, W8TEE and ALPS AC8GY not only developed their own software defined transceiver, but have also made their design open so that radio amateurs can build and experiment in their footsteps. Jack and Al, welcome to Tonight at 8. Can you give us a quick preview of what you'll be talking about this evening?
We'll be happy to. I'm Jack Purdum, and the handsome dude over here is Al Peter. Yeah. And tonight we're just going to give you a quick overview of what the T41-EP is, how we designed it, and some of the things and features that are part of it. Go ahead. We're done. We'll wait.
That's brilliant. All right. Well, we're looking forward to it. And before your presentation, a reminder that if you at home are watching this on Monday, the 15th of May, then this is live and you can ask questions or make comments on either BATC or YouTube chat at any time during the presentation or straight afterwards. Please include your first name and call sign if you have one within every message. And note that you can make this video stream fill your screen on most devices, usually by double clicking on the picture or pressing the full screen button. But now, back to Jack and Al to find out more about their T41-EP transceiver project.
First of all, thanks for having Al and I. We appreciate it. And we have sort of a love for the RGSB, or RSGB, sorry. And what we want to do tonight is just give you a quick overview of what we call an SDT. And a lot of people aren't familiar with the term SDT, and we use that for a very real reason. It's a software-defined transceiver, which is distinguishable from a software-defined radio. This is a picture of our beta version, I guess you'd call it, of the SDT that we made. This is probably 2 years ago. And it has just some of the features so that you can recognize them later on in the discussion. On the left upper is the display, which is a 5-inch display, and the radio will support 7 or 9-inch displays as well, but the 5-inch is what you see here. The four encoders in the middle, you can see volume, and that's exactly what you would expect it to be. The center tune is a little different in that it centers the tuning frequency in the middle of the display, and you can see Al marking where it is. The fine tune display moves the filter block, which is shown in blue, up and down the spectrum from low to high. And if you would go all the way to the left or right end, it will reset itself at that new end frequency back into the center. This is sort of the way the Flex does it and some of the other software-defined radios.
We'll hopefully try to demonstrate this at the end of the talk.
The fourth encoder is called filter words per minute on this display. We've actually changed that to filter menu. And the reason is because many of the menu choices are hidden. In the top left of the display, where Al is pointing now, are the primary and secondary menus, and they will appear for those things that don't get changed very much. Everything that you would expect to be changing during a QSO appears in this 18 push button matrix that you see over here. The menu up and menu down advances the menu. Band up, band down does exactly what you would think. And then the other things are more or less specific to our radio. And one of the important buttons is the select button, which is in the upper left, and that activates the menu choice. So that's kind of a quick look at what the rig looks like. We do want to make a distinction between SDR and SDT. SDRs are usually only receive devices. They range all over the map. There's $10 dongles and SDR Play. Al and I both have SDR Plays, and they are very, very nice, but they also cost about $200, so they're much more expensive. But they're still only receive. An SDR radio is a division between hardware and software. If you go back to the old days when I first got my license, SDR didn't exist, and everything was implemented in hardware. Well, then if you wanted to make some enhancement or improvement in the way the radio operated, it meant tearing into the hardware, which is a fairly expensive proposition. The advantages then that an SDR has is, well, the first one is you can replace the high-cost hardware components with relatively inexpensive software. True, you have to have memory and a processor, but it's relatively cheap. The SDR that we use is the Teensy 4.1, and it's a very, very robust processor with almost 8 megabytes of memory and 1 megabyte of RAM, and it runs at a clock of 600 megahertz. That's about, 30 some times faster than the Arduino Nano. So it's a very, very capable processor, and it costs $32, so it's fairly inexpensive. The other thing that SDR radios offer you is the ability to enhance the feature set over time without necessarily changing the hardware. Most of the changes can be done purely in software. Our design goals. Al and I guess it was 2019, we were at a field day over in Indiana, and on the drive back, we started talking about having an SDR that would be portable, not necessarily portable in the SOTA activation sense of the word, but portable that it would be easy to take with you. And we decided that one of the things that we wanted was to have a high frequency software defined transceiver that would cover the most common amateur bands as far as use goes. We also insisted that it be both single sideband and CW. Small CW transceivers like Hans Sommer's QCX, very, very popular. I think he's got something like 10,000 of them now in the field. But unfortunately, there's a small population that still uses CW. So we wanted it to also be able to handle single sideband. The T41 can handle AM reception, but it cannot transmit on AM reception. We do not do the digital mode, but there's enough resource depth in the transceiver to add that if you wish to do so. I call it a fuzzy QRP, and the reason is because it's user selectable from 1 to 20 watts. The exception is on 12 and 10 meters, it drops down to about 10 watts. And that's because of the choice that we made for the final transistors. And the other good thing about the T41 is that it is self-contained. It doesn't require a PC or a laptop or a tablet for the display. Most self-contained rigs that have their own display, like the Zygo G90, the display is about 1.25 inches across, and it's very, very difficult to read. And also, the band spread is limited to 25 kilohertz. The T41 uses special ADC and DACs that allow us to show a band spread of up to 192 kilohertz. So that's a big advantage too. It's what we call trunk portable, or you guys might call boot portable. Unless you're an Olympic athlete, you're not going to run this thing up and do a SOTA activation because it's going to weigh about 2.5 to 3 kilograms.
And the problem, Jack, is that the battery weighs about 3 times what the radio does.
Yeah. So we're not recommending it for portable operation unless you can take this stuff and set it up on a picnic bench near your car, or throw it in the trunk or the boot and take it on vacation to a cabin or someplace like that. So we did not attempt to make it a rig that you can stuff in your shirt pocket. We think it's priced at reasonable cost. When we started this about 4 years ago, the cost was under $250. And because of supply chain problems and general increase in costs, it's going to be probably $100 more than that now, around $350. If you have a good stock junk box, it might be less, but we use surface mounted components, so you might not have those handy. The other thing that was mentioned at the top was that it is an open source project. And what this means is that we have made all of the schematics and the Gerber files for printing the circuit boards and everything else available to you. So if you would like to make your own circuit boards, you can. Other people are selling circuit boards.
Just as an example, I think you might be able to see these. I'm not sure. These are two of the circuit boards. They're up and coming. This is a version 12 that I'm currently working on. The boards are all about this size or smaller, and there's a good reason for that, which we'll talk about later.
Okay. This is what the main screen call out looks like. And I told you before that by default, there is no primary or secondary menu. Those come up as blank fields when you first start the radio. But certain menu options that you can activate with menu up and menu down on the switch matrix will activate. So if you did CW options, the first option in the CW field is to set the words per minute. And it's a bad photograph, but that shows words per minute. If you then hit the select button that's in that 18 matrix, it will then change the word per minute field to a number. And then you just turn that menu encoder and dial in the words per minute that you want, press the select button, and off you go. The primary frequency is VFO-A, but it has got two VFOs, VFO-B, and the active VFO is printed in gray and is in slightly larger font than the inactive. We also show the time and date on the display as well. Then the band information shows the center frequency, the band that you're operating on, the mode you're operating in, the upper and lower sideband, lower in this case, and the power output. Power can be set through a menu varying from 1 to 20 watts. The filter overlay is shown right here as 3 kilohertz. It's a negative number because we're using the lower sideband. And then if you go over to the audio display, you'll see that that line shows that we're using a 3K filter. You can use the filter encoder to change that width to up to 6 kilohertz wide or down to, I think we set it to 1.5 kilohertz on the low side. And that is a real-time plot of the audio being received by the receiver. So the little bumps on the spectrum display are actually being recorded over here on the audio display as well. The waterfall, of course, is like any other waterfall. It tracks the signal, but we use a fast Fourier transform to set the spectrum display, which is the frequency domain, and then the waterfall is in the time domain.
No, it's a time history, Jack.
Time history.
It's still frequency, but this way.
But through time
history.
And we give you about 30 seconds,
something like that.
Almost 30 seconds of time. And you might say, well, why would I care why this shows me 30 seconds ago? The reason is because during contests, someone will turn the mic off while they listen to a reply, but you'll be able to see in the waterfall where they were, and then they'll come back on at the same spot. So if you're doing a hunt and pounce, the waterfall can be your friend to easily locate what's going on and where. Back in the filter audio filter, you can see two vertical lines, and those are the Gertzel band. And that's used by the CW decoder. In other words, we try to get the peak audio signal centered between those two lines. And when that happens, the sweet spot indicator will come on. There's a block there that's not turned on right now. That will come on, and then the decoded signal will appear below the waterfall as the code is translated. Let's see, what else? The receive indicator and S meter, you've all seen those things before. So I think we're okay there. Okay, the architecture. We tried to move as much functionality into the software and remove it from the hardware as possible. We use a quadrature sampling detection system using a Talo detector. It's low cost, low insertion loss, and it's fairly easy to implement. And so that was what we went with. The digital signal processing functions in the frequency domain, mainly because of efficiency. The filters are, I don't know if you've heard the term brick wall, but if you look at it, they are shaped very much like a, what the Devil's Tower. It almost looks like a block signal generator type.
Yeah, the skirts are
extremely steep.
sharp. They're like, I calculated once, it's like close to 200 dB per octave. If you're used to analog filters, they're more like 12 to 18 dB per octave. So they're very sharp. And they're used for two things. The filters provide some help if you have a high frequency noise that you want to get rid of, so you can improve the clarity. But in the digital signal processing, it also is used to select between the upper sideband and the lower sideband, and the filters are sharp enough to do that. If you know anything about analog SSB architecture, many times the lower and upper sidebands are chosen by crystal filters at an IF stage. Well, we have a direct to baseband here, so we don't have that, but we have something better, and these are much sharper than most even crystal filters in an IF. So yep, they're very useful.
The other thing that we did was we weren't happy with the built-in analog converters that the Teensy has, which are, they say 12-bit resolution, but actually it's 10. So we put on external DACs and ACs to boost the bandwidth possibly up to 192 kilohertz. We don't recommend using it at that level, but it's there if you need it.
And the bit depth is probably 20 bits instead of 12.
Yeah, and it makes a huge difference on the bandwidth that you can look at.
Well, the bandwidth and also the resolution that you get in the audio resolution.
Screen resolution too. The functions, we went with the push button interface for several reasons. One is we don't like to spend our time wading through menus, and that's frequently done on most of the popular commercial rigs. We find that the 18 buttons that we have on the Matrix work fairly well for almost anything that you'd want to do in real time in a QSO. The other reason that we don't use a touch screen is because even with a rather heavy heat sink, the T41 doesn't weigh much, and if you go poking around on the screen, you can actually scoot the rig across the desk. But we find with the push buttons, I can take my right hand, and if I had to, I could put it on top of the T41, and my thumb is long enough to reach all 18 buttons, so I can dial it without having to worry about moving it. But actually, the push buttons are sensitive enough, you don't need to worry about that anyway. The modular design, the hardware is designed and centered around 7 major printed circuit boards. And we did that for 2 reasons. One is
Let me show you the
Yeah.
interior of the unit while we're talking about this. This is the interior of the T41. This happens to be one with a 7-inch screen. You can see the individual circuit boards. This is the receive RF board. This is the main board over here. This is the exciter board, filters, and the power amplifiers in the back. It's all modular, so if anybody wants to change something, it's very easy. You just do your design and pop it in.
Yeah, if you're unhappy with the performance of our PA board or whatever, filter board or whatever, just pop ours out and put yours in, and off you go. The other thing that we've done is we have limited the size of the boards to 100 by 100 millimeters. And we did that because most of the PC houses have special pricing on boards that are that or less. Okay.
This, I'll talk a little bit about this, and I won't go into the detail that you might expect from a plot like this. But what we basically wanted to show, this is the receive process, and there's a similar one for the exciter process for the power amp out RF. But everything that's in the colored block here, all of this stuff is all done in software. And those things that are outside that, like this and these things down here, are hardware. So what you can see is that most of the processing and most of the guts of the radio is all done in software, which meets our design goals. So you can go in here and make changes to the graphics if you want. You can change the filtering and whatever else, but it's all done in software. So the net result is a very nimble and flexible design. This is the modulator, a little different color scheme, but everything in this segment right here in the tan is done in software, and the rest of these are the hardware pieces that go out. Again, similar design philosophy. Most of the important stuff is all done in software. Jack talked about the filters and the bandwidth, and this is a plot that was taken. It's actually the RF output of the system around 7 megahertz. 7 megahertz is in the middle here, and there's a 20 kilohertz band across here. So what we have is the upper side band, and you can see that around 0 in audio frequencies, if you're tuned to 7 megahertz, you get nothing. Jumps up around 200 hertz, nice and flat out, in this case, to about 2.5, 3 kilohertz. And then here's this brick wall again. So any information that's noise that's outside of the band disappears, and all of the lower sideband is gone as well. So these filters are very good, and they're all, again, done in software.
All right. Go ahead, Al. You're
okay. In order to do decent transmission, you need to have good filters. And we have filters in the output. We have 2 sets of filters. We have a filter that's coming out of the exciters, so the signals that are generated that go to the power amplifier are filtered. And then after the power amplifier is out, they're filtered as well. We have modified Butterworth filters. I'll show you a plot of those in a second. And we've made it modular again so that the popular QRP Labs filter kits can be used both in the pre-filters and the external filters. You don't feel like doing your own. We use relay switching. We tried pin diodes, but weren't quite as satisfied with the results as we might have been. This is a plot of one of the filters. This would be the one for 7 megahertz again, the 40 meter band. Here's the 40 meter band. This is a low pass filter, and we have 10 dB per major division over here. So you can see it comes out to about 8 or 9 megahertz, then falls off greatly. Whoops. You hit the button. This is where the second harmonic would be of the output. You can see it's down about 30, almost 40 dB. So any residual harmonics are pretty well eliminated by this, and all the other filters are quite similar.
Yeah, you get the numbers at the bottom.
Yeah. The power amplifier is built around inexpensive MOSFETs, the popular IRF 510s. They cost less than $1 each. And we get 20 watts out on SSB and CW on most of the bands. We have thermal protection built in. And if you want, you can use current limiting, but we have a boost supply for the finals so that you get enough power. And most of us have current limiting. And so most of the guys who build this don't use the built-in current limiting. You can if you wish. This is the power output for band. And we said it's nominally 20 watts, which is down here. But what we find is that on a couple of the bands, you get up as much as 35 watts with decent signal clarity. So it really is doing better than we said. Talked about the output at 25 watts, 7 megahertz. The worst case scenario, which is the third harmonic, is down 44 dB in this case, going through the filters. This one didn't use the pre-filter. With a pre-filter, it's even better. So we're well within the regulatory limits for these harmonics. Jack, you want to talk about the building?
Okay, the packaging, we're talking about the case, and that's going to be totally up to the builder because they might opt for a different display size than the 5-inch. This rig, the T41, is being offered as a kit by 4-State QRP group, and they're out of Missouri, and they will be demonstrating that at Hamvention this week, actually.
Yeah, it's this week.
And I don't know if we have a picture of
We
that.
do at the end.
Okay, we have a picture of it at the end. The big thing that makes this a fairly large package is we need a hefty heat sink to dissipate the power coming out of those finals.
It's a typical heatsink that were used. This one happens to be rescued from an old PC, and it's hefty enough, and it's got enough area on there to keep the power amp quite nice and cool.
Okay.
Also cheap, because I rescued it.
Mentioned that the multiple boards, none of them are larger than 100 by 100, which should make it pretty easy to substitute with a new board if you wish. There's lots of empty room on the boards.
Well,
the main board's getting pretty dense now.
Yeah.
We took, Al took some of the modules that were small boards and took them off of those small boards and put them directly on the PC board.
Well, also we have coming out, it'll be in about a month or so, version 12, which takes two of the boards, takes the receive board and the exciter board and puts them together on one. This is something that was requested by some of the early adopters of this, and it's got some performance improvements that make it useful.
Yeah. Boards are easily, we've already covered that. This is a better shot or an easier to see shot of how we have mounted the boards. Al created this scheme. Everything you see is pretty much 3D printed. And then he has brackets that bolt to the bottom of the case, and all of the boards are mounted vertically.
Yeah, there's a lot of space saving if you do that. Interconnects are with ribbon cables, and these are, in this case, RF SMA connectors. These are just three of the boards that you show here on a prototype setup.
Well, this is the 4-states QRP group that I was mentioning before, and it's a semi-kit. And what I mean by that is all of the SMD devices on the boards are already soldered in place. So really building the radio reduces to connecting up the switch matrix and the encoders and the cabling between the boards. And this is a picture of the 4-square QRP kit that they're going to be offering.
It's a prototype.
This is a prototype of, it's almost 8 or 9 month old.
Yeah.
It's been around for a while. Al built this prototype. And you can see the layout is very similar to the one that we advocated at the start of this presentation.
The nice thing about this, the kit will include the case, and the case is made of printed circuit board material, but it's been etched with the display, I mean the front panel designations on there. So they'll be ready to go and just clamp it together. Before we get to the questions, I want to give a short demonstration. Hopefully there'll be something that we can actually see and hear. So let me move the mic and move the camera around so that you can see the front. So this is a 7-inch version of the T41, and we're on 40 meters at the present time. There is some stuff going on here, so I'll turn this up.
What does that mean? It's an Latin word for what? Light in? That's right.
So in this case, you can hear both sides of the conversation. Now, as Jack mentioned, I'll just demonstrate a little bit of this. We can change the center frequency. And if you look here, right now, the center frequency is on 7.154. That's where this guy happened to be parked, and he's been there for the last hour. I can change that center frequency with this encoder knob, and I can change the increment. And right now, it's set for 10 kilohertz each time I click the knob. So it's pretty quick to move anywhere around in the band. For most of the lower bands, we have either 100 kilohertz across here or about 200 kilohertz, which covers typically either most all of the 7 of the 20 meter and 40 meter bands, or if you put it down, the 2X, which gives you a little better screen resolution, about 100 kilohertz. So you can see it's quite nice, and you can move around this very quickly. So if you want to get to one of these up here, it moves the center frequency immediately. Now, we talked earlier about the waterfall display. So you can see on the display how the time history is being preserved as we go down. This guy went away, but I could easily move up there and pick that. Now, the other knob that we have over here is the knob that moves the fine tuning around. And I have a couple of increments on that, so I can change that. Let me just tune to this one real fast.
Yeah, and also should point out the center frequency right here is not changing from its initial position.
And this time.
But you'll notice that the use of the fine tune does move the main frequency display. Now, if you want then to park it on that frequency, you would hit I think it's this one. And that sets the center display to that new frequency. So now we are centered on 168.
It moves everything.
It moves the entire X-axis display.
This is the volume control. And I mentioned earlier about the filters. So if you look over here on the audio display, this is the top end of the filter, and I can change that in real time. You can hear the difference. So you lost all the high frequencies. Then I can bring it out here.
That comes in very, very handily on, well, obviously crowded band conditions. But I find it useful when I have 2 CW stations working close to one another.
The other thing we have are some DSP operations. I have a noise filter. Actually, 3 of them.
Built up so many, people moving in from Jersey and from New York. That I'd say about.
So this is without the noise reduction. And this is with the noise reduction.
And we're updating the window down here to tell you what's being changed.
We also have a notch filter. It's automatic. There was a tone in there. It would automatically get rid of it. But we can change things about the display. We can change the mode. We talked about the menus. I can demonstrate that. So I can just page through the menus, and you can see them in the top up here.
Oh, we forgot our ad.
Yeah, we'll get that. So, for instance, the CW options, I press this button, then it comes up. You can't see it on there, but it says words per minute. And I change this, and it changes the words per minute. And that's for the decoder.
You have to select it.
Yeah. Jack didn't even talk about the decoder. He's got a really nice CW decoder that's built into it, and that displays across the bottom down here when it's operational. We're not going to try to do that right now. We bring out the various external functions. So you got the phones, a mic, push-to-talk key. Mike also has a built-in push-to-talk as well. That's pretty much it at this point.
Put that back in. Al mentioned the decoder. It's called the ALPS decoder, which is Al and Purdum. I'd like to take credit for it myself, but since Al's sitting here, I can't do that.
Nice guy.
But Al came up with some really clever stuff that draws upon correlation analysis, the hypergeometric mean, Gertzel algorithm, and then we have a binary search quick lookup involved too. And the result is, rather than taking 10 to as much as 30 seconds to catch up, the ALPS decoder can catch up usually in 2 or 3 seconds. So
now we're gonna do an unashamed
folk
little ad right here. We're not doing this necessarily to sell the books, but what we'd like to do is point out that everything that we talked about today is all covered in this volume, which is available on Amazon.
And Amazon UK too.
It's you won't be able to see anything much here, but it's 500, nearly 500 pages of material like this with diagrams. There are various printouts from the performance. There's code in here and description of the code.
Well,
and references.
The purpose of the book was to present a readable introduction to digital signal processing and to explain how the radio works. That was the first edition.
Actually, the way it started out was we were talking about a book. And my idea was that what we wanted to do is try to explain all of this stuff in a way that's accessible. When I began learning about SDR, I found out I had to go everywhere in the internet and references to get the material that was necessary, and nobody brought it together. And say, fine, some of the books, like the Lyons book on DSP, has all the theory that you ever want, but it stops short of developing code. And then some of the other people have code out there, but they don't talk about some of the intermediate steps. So they say, well, you got to develop a filter, and you need the filter parameters. Where do you get those parameters? And that's not explained in the same place. So we tried to bring it all together and step you through the process of what it takes to understand and to build one of these SDT radios.
We spent a lot of time on the book, and
4 years.
4 years. It's paid off in that we have over 120 reviews, and we have a 5-star rating for the book, which is 5 out of 5.
4.8, but
It's 4.8, but it's classified as 5, and that's very unusual for a technical book. And the other thing is, we wanted it to be readable so that it kind of sounded like you and I were sitting in a room together talking about this stuff, and we didn't want it to be stuffy.
So there's not much math. There's enough math where it's needed, but when we get to the point of needing math, we say, look
at the reference.
If you want to do this, here's the reference to go to, either being a paper or some reference books.
I tried to find the email that a guy sent me, but he's a professor at a college here in the U.S., and he has an Intro to DSP course, and he's going to use our book as a textbook. So I think that augurs well for the content of the book. So enough of that plug.
Well, we are, I think, at a point now where we'd like to take some questions if anybody has any.
Sure. Thank you very much, both of you. A real good whistle-stop tour around your transceiver there. Really an amazing development. Anyway, if you're watching this at home and you've got any questions or comments you'd like to share and you haven't already done so, please do it now on either YouTube chat or BATC messaging. And please don't forget to include your first name and your call sign if you have one as well. I mean, you did touch, Alan, Jack, if you did touch on why you did it, and it seems like you even maybe started, originally you intended just to write a book about it, but you've got a project to show. Is that right?
Yeah, I think so. The idea was we had a previous book that we had done together on projects, and we thought, well, I'm not going to do another projects book, but we'd like something a little bit more in depth. And as I said, there really wasn't, in my opinion, the text that went from A to Z in the whole thing, from the theory to building and developing the receiver. So the receiver came along, or the transceiver came along, as a result of illustrating the various topics in the book. Yeah. And it turned out to work reasonably well as well. And also,
well, and the tie-in with a real-world circuit makes all the difference in the world. Abstract discussions are fine, but it's really nice when you can beat on the hardware as well.
Yeah, sure. Now, you mentioned your book, and I did actually check earlier, and it is available from Amazon.co.uk as well as Amazon.com. So it's available at about £28 in the UK price. But a book's very good, but having said that, especially to download software and things like Gerbers for the PCB designs and things, people need to know where to get them. So is there a place that they can go on the web to download lots of this information if they don't want to go into all the depths that the book does?
Yes, just go into your browser and into the search, type Software Defined Ham Radio, and that will take you to our website. And all of the files, the Gerber files for the PC boards, the schematics. We're in the process of taking all of the images from the book and uploading those because they're bigger than they are in the book, of course. And all the software is there too. We have a new version of the software that will probably be coming out in a couple of weeks, but the latest software is there already. So once again, that's Software Controlled Ham Radio. If you search under that, that'll take you to our IO group, and you can join. We have about almost 3,000 members now, and it's a great place to ask questions. A lot of people will print a 10 run of a board and offer the other 9 for sale for next to nothing. So it's a great way to buy things inexpensively too.
Sure, it's very good. Thanks. And we will, for those people watching at home now, we'll be putting this a link to the IO groups on our website as well, on the RSGB website within a few days, so that you can easily click and find source of that. Anyway, we've got some questions and things for you, so if you're ready for them, we start with Mark, G0TMT, and he asks, any plans to include CAT interface?
Well, I think we're at a point with this where we'll be doing some enhancements, but we're going to leave some of the things like that to the experimenter clients. One of the things you've noticed in the title, it's T41-EP. which means experimenter platform. And we would like to encourage anybody who desires to do that sort of stuff just to dig in and then make it available to everybody else. So there are some things that would be nice to have. We may or may not do that.
As we mentioned earlier, the T41 has a very deep resource pool. And as it stands right now, we have almost 8 megabytes of code space. And right now we're using less than 5% of that. So if someone wants to add something, there's plenty of room. There's plenty of resources to do that. The other thing is we've been working on this for 4 years and we're getting a little burned out, to be honest. We'd like to just sit back and play with it now rather than think around with it like we have been for the past 4 years.
Yeah, and I guess it's rather nice to encourage other people who might have different ideas and different aspirations for it to actually collaborate, and it becomes into a much bigger design, doesn't it?
We've really benefited from a lot of that because many people have fed back to us things that they would like, and we've got some features in here, and I can show you just one of them real fast that was contributed by one of our builders. And that is if you want to put in a frequency that is
like
not
WWV or something,
not part of it, you simply press the button down here and it goes into a direct input mode, and all these buttons then become inputs to it. So you press whatever you want on here, and then you press the select, and it automatically puts that up. So if I wanted to do the 10 megahertz, so I'd press that, and I see here where I am. Well, I guess I one up. There's 1 and a 0. No. I'm doing this around the corner, so it's a little less convenient. Now, there's a 0. So that's actually 12, but that's okay. And I hit this, and it pops up automatically then to 12 megahertz. It tunes the radio to that.
By the way, if I'm not mistaken, this was given to us by a guy in Britain.
Yeah. So he provided the code, and we took it and
squeezed it in
with his permission. Put it in.
Okay.
We're not as well organized as you are, David.
That's all right. We've got more than one camera. I think you're doing very well with one camera in there. I mean, you mentioned briefly at the end about the CW decoder, and of course that's one of the things that we were particularly excited to learn about. And you mentioned about how quickly it can resolve CW in a few seconds as opposed to 20 or 30 seconds. Can you elaborate a little bit more about how you developed that CW decoder? Is most of the clever stuff, if you like, implemented in the firmware, the software side of it?
Okay, what it starts with is we take the signal in and we convert everything to I wish we had that diagram. It's in the book. There's an entire chapter on the decoder in the book. But essentially what we do is we have a signal that comes in, and we look at it, and it's usually pretty jagged. It looks like the ALPS viewed from the side. And what we do is we take those signals, those CW signals, and we drop down from 27,000 feet to 15,000, and we run a knife across it, and that puts flat tops on all of those signals. And then we look at the width of those signals, and if it's 1 dit length, it's considered a dit. Let's see if you can see it.
Yeah, you can see that.
Yeah, you can see where it's flat topped over over here. And we then measure everything in terms of a dit length. So 1 dit length is a dit, 3 dit lengths is a DA. Spaces are, an atom space is 1 dit length, a character space is 3, and then word space is 7, and so forth. So we do all of that, and then we correlate that with a correlation coefficient of 0.15, and then everything that's above that is treated as a signal, and everything below 1.5 correlation is called noise and ignored.
So this is the the flow diagram. I'm not very good backwards here. This is the flow diagram for the process. You can't read it, but there's many steps involved in going from the raw signal to the output.
Very quickly and very simply. We get a bimodal distribution of dits and DAs, and we use a hypergeometric mean to slice those in half. So the lower half is a dit, which would be 1 dit length, and above the hypergeometric mean is considered to be a DA. And from that point on, then we use the Gertzel algorithm to sharpen what is measured as dits and DAs.
And this is the printout at the bottom. If I can get the camera over here.
If you move it to your left, Al, I think that will, yeah.
You see at the bottom there's a printout, and that scrolls across the screen as it goes. And we've decoded, 35 words a minute or something like that?
Well, actually, if it's a clear signal and somebody has a good fist, and that's another thing, no decoder is going to be able to cope with the characteristics of a fist. Some people will, especially if you're sending with a hand key, but even if you're sending with a bug or an electronic keyer, we can actually see in the decoder, watching a conversation over a period of a half an hour, we can actually see the guy get tired, and we can see his code get sloppy as time goes on. So no decoder is going to be perfect. It's just not going to happen. But we think that this one's pretty good.
Okay, Rachel M1AYG asked a question about what method you've used, and I think you've probably answered it. Hopefully that's enough for you, Rachel. She's very, very keen and says that she's probably going to go and buy the book, actually, so that'll help to understand how it works. Steve M1SDH says, wow, amazing work, Jack and Al. What part of the development of the T41-EP did you find the most challenging?
All of it.
I think the thing that's taken the most time, I think you might agree, is the power amplifier.
Power amplifier is problematic, and one of the reasons for that was that in our design criteria, we wanted to make this inexpensive.
Yeah.
And so we opted for the IRF 510s, which cost $1 each. There are better transistors out there which would have made life much simpler, but they cost $8 to $15 to $20, $30, $40 each. And in the process of developing this, I had a whole pile of dead IRF 510s. That
it's a good job they weren't. You didn't use the $10 and $20 ones, then, isn't it?
Yeah, that's exactly right. There are third-party folks out there who are developing amplifiers that will probably work with this, using those higher performance transistors, and they may work better. We have something now that works. It's not ideal, but it does work, and that's one of those things where the experimenter platform would be useful for somebody to develop a better one.
Yeah, one of the things that they would probably gain with one of those high-priced transistors is you would have a flat power curve at 20 watts all the way across to maybe even 6 meters.
Out of 10, certainly.
Yeah, I mean, from my knowledge of the IRF 510, I mean, it's not even really meant for RF, is it? I don't think. So you've done really well to push a switching transistor, from what I remember my designs over the years, into using it for RF at all, and of course kept the cost down as well, as you say. We're coming towards the end, I think, now. So if you've got a question at home or a comment, or maybe you've seen or used one of these, then please enter them now onto YouTube chat or BATC messaging. Got another question from Jeff, KS0JD. What is the basis of your code, i.e. what language do you use?
Oh, I've been using C since the late 70s, and I don't know how many books. I've got 20 books out there, and I think almost all of them are on C. So that was a natural choice. Also, we stood on the shoulders of Frank Dyzuk in his group, who wrote the convolution SDR.
That's DD4WH.
And they did a great amount of work for the receiver part. There was no transmitter part in that code. But it was a job. It was a good place to start because we could stand on their shoulders, but those shoulders were 18,000 lines of C code all in one file. So the first thing that we did was we broke it out into like 22 files, and we chopped a lot of features out that we didn't want, and one of them was RIDI. So we ended up with about 11,000 lines of C code spread over 20 files. And then we started adding the transmitter code, and I think we're up to maybe 14,000 lines of C code now. And believe it or not, I have not memorized them yet.
I'm not surprised. Well, that's virtually it, gentlemen. Thank you very much indeed for today. It's worth mentioning again, you did mention it before, that at Dayton this week, your transceiver is on display by 4 State QRP, I believe it was, from Missouri.
Correct.
So
Correct.
if you're going there, whether you're from the UK or this broadcast worldwide, so wherever you're watching this, if you're heading to Dayton this week, that'd be a good place to see it. We should also just mention at the end as well that you're no strangers to writing books and things, because indeed the RSGB offers one of your books itself. I think we can just show you that now. This is one of the books that you wrote a couple of years ago, 2019, I believe. Here we are. This is Microcontroller Projects for the Amateur Radio. I guess that's a good maybe book to get started with, the idea of using computers and radio.
There's some good, interesting projects in it. That's ours, right?
Well, there's another.
And it's a good book to get started with using microcontrollers.
That one is ours.
And
yeah, it is yours, definitely, gentlemen. Yes, that's certainly a book that you wrote. Yeah.
Well, and the good thing about it is that a lot of books concentrate on just one processor, and that book has projects for the Arduino, the STM32, the ESP32, and the TEE. So that's a good introduction to all of the.
I just thought that might be a softer entry for people. So that's available from rsgbshop.org and also ARRL if you're watching it from the stateside.
Right.
So once again, many thanks to both of you, not just for tonight's presentation, but for all the work you've put into this project and then making it openly available to the ham community, because I'm sure there's some people there who are going to whet their appetites. Maybe Mark will get on to designing a CAT interface. You never know. So thank you very much indeed to both of you. Lots of people, by the way, thanking you online, and we're really grateful for you joining us tonight. All the best.
We appreciate the opportunity, David. Thanks.
Thank you very much, Alan, Jack.
See you later.
Bye now.
Bye-bye. There we are, and that concludes this webinar. And thanks once again to our guests, Jack Purdum, W8TEE, and Al Peter, AC8GY, and also to the team who put this series together behind the scenes. We hope you've enjoyed this Tonight to Date and that you'll be able to join us next time when Mike Richards, G4WNC, will join us to talk about Node Red for radio amateurs. Now, if you'd like to see details of future webinars or watch recordings of previous programs in the series, please visit rsgb.org/webinars, where you can also send us comments and feedback. And finally, if you subscribe to the RSGB's YouTube channel, you'll be notified of all upcoming Tonight at 8 webinars, as well as other new videos and presentations from the Society on a wide range of amateur radio topics. But until next time, this is David G7URP signing off and clear. Bye-bye.